Hi, my name is Aaron Dales, and for this week in lab we had to go out into the real world and observe two falling objects, one that fell at a fast pace and one that fell at a slightly slower pace. The objective was to observe the effects of drag on the falling object. For my slower paced item, I picked a Kleenex 3-ply tissue, and for my fast paced object, I picked a plastic poker chip. The result was that the slower moving object had a larger constant of drag force, which explains why the tissue fell at a slower pace, because the drag force was greater upon the tissue than it was on the poker chip, which caused it to, since drag is in the opposite direction of the force of gravity, caused it to fall at a slower pace, whereas the poker chip had virtually no drag and fell at a theoretically normal pace. I used tracking software in order to record and analyze the falling of the poker chip and the tissue. The poker chip was about 11.5 millimeters wide, which I measured up here, and I converted that into meters in order to get accurate data for this experiment. Using tracker software, I was able to pinpoint the middle section of the poker chip each frame as it fell, which lasted about 7 frames. And then using this data over here, I was able to import it into an Excel file for gravity and come up with the experimental data for the poker chip, which is represented by the blue dots here. A similar process was done for the tissue, but its fall lasted 8 frames and it had a width of 109 millimeters, which I then converted into meters again to get this data here and put it back into the same file to get this graph over here, which is a position versus time graph for the tissue for the fall of the tissue. The red dots you see here were computed using an experimental model in which to compare the experimental data to the theoretical data to match up and also find the constant of drag force. Sorry, this is the wrong graph. This is my actual gravity graph for the tissue and the poker chip, whereas the other two I showed you before were for the drag forces. So in order to get the theoretical data, I came over to this model program, which we created in order to calculate the position of an object under certain conditions. So this one would be for the tissue, which had a mass of about 0.000756 kilograms, and it had initial position 000 and no initial velocity. I chose delta t 0.01 for the time step because the fall only lasted about 0.29 seconds, and having 29 steps really allows you to see the arc of the ball as it fell, or in this case, tissue. So in this scenario, the only acting force upon the ball is gravity, and since gravity is the only force, we were able to calculate the ball's velocity by taking the F net divided by the mass of the ball, because we all know that force is equal to mass times acceleration, so this gives us the acceleration times the change in time would equal the new velocity, and to update the ball's position, we have the ball's initial position plus the ball's current velocity or final velocity times the change in time, which would update the position of the ball. And here's the program. So as you can see, the ball fell a short distance, and we have a nice little arc here. The data was then extracted from a Excel file created from the Python program and input into this Excel file where you see the red dots for both the tissue and the poker chip. Here's the model for the poker chip. It's very similar. Hold up. Alright, fixed it. Minor programming error. But anyway, here's the real fall of the ball and the position versus times graph for the poker chip. As you can see, it lines up very nicely with the experimental data. The process for the theoretical data was run again in these two Python programs, except this time we included the drag force and added it to the FNet and calculated, or guessed rather, the constant of drag force until we found similar results to the experimental data. Once we calculated the constant of drag force and got similar results to the experimental data, we put it back into another Excel file and created a new graph to demonstrate the drag as well, the drag model of the experiment. Here we have the experimental data in the blue dots and the theoretical data with the drag in the red dots. Here's the tissue and here's the poker chip. These are both position versus times graph. What I found to be interesting was the difference between the drag force graph of the tissue and the gravity force of the graph of the tissue. Whereas the gravity force theoretical hits the ground before the experimental data, the drag graph hits the ground about the same time, and it takes longer. So because it took longer to hit the ground, the tissue must have been moving at a slower velocity and must have had a greater force of drag, which we confirmed through our model because it did in fact have a greater force of drag compared to the poker chip, which had virtually little to no force of drag on it in the experiment when comparing the experimental data to the theoretical data. So what does it mean? Which models, if any, predict a terminal velocity for the slower moving object? So first, let's look at the tissue minus the force of drag. Without the force of drag acting upon it. The graph doesn't demonstrate any terminal velocity. In fact, it's curved throughout. However, when we do add a force of drag, the graph becomes less curved at the end and looks more like a straight line. So it would predict that a terminal velocity it will reach terminal velocity eventually. So what if, for the object that drops slowly, using the models I made, we examined it as a function of time? Basically, if given an initial velocity, does the slower moving object reach a terminal velocity? So the first one took out the force of drag, gave it an initial velocity of -2. In the model, it's still curved, it's not exactly a straight line. So I would say that without the force of drag, it does not reach a terminal velocity. But, as we see when we do when we do add the force of drag to the equation, there is a straight line almost, and it basically reaches terminal velocity from the beginning. So, if given an initial velocity, a object would reach terminal velocity faster because it starts off closer to the terminal velocity and less force would be necessary to reach the terminal velocity. And there you have it. Hope you enjoyed my lab.